Okay. So, general announcements. You're not gonna have class on Thursday because it's Thanksgiving. I hope you all have a nice Thanksgiving. We will be having our fourth test on chapters 6 through 9 next Tuesday. So next week on Tuesday, we have the test. It'll be like the previous tests, 60 questions, in person, multiple choice on Scantron sheets. Your presentations and papers are due, so the last homework and the last set of worksheets are also due on the 2nd. So those you need to submit on Brightspace. Your presentations and papers are due on the 4th. Those you also need to submit on Brightspace. So let me show you where they are on Brightspace. There's an assignment for the presentation. There's 2 separate assignments, one for the paper, one for the presentation slides. Why is this so slow? So if you go to content, semester project. The semester project report is for the paper, 2 to 3 page paper. The semester presentation, 5 to 8 minute PowerPoint presentation. You have access to PowerPoint, so you can do the slides and submit them. And you need to be able to submit the slides in a format I can read, and then I'll do and have them submitted in some way, have them available for when you're giving your actual presentation. The schedule of presentations is right here. And it's just the order there, the arbitrary order I set up. It literally, I just randomized the class order. So you can know when you're actually scheduled to present. Since there will probably be time at the end of the earlier days, if you want to present early, you can. But make sure if you submitted your slides in a PowerPoint format, I'll be able to download them, so that won't be an issue. I will download all the scheduled presentations before class on these days. Yeah. That's most everything. Any questions? Okay, then I'll continue on with chapter 10. So we talked about glaciers. Glaciers will also, because glaciers can pick up material and carry it, they can deposit it. And this is called glacial till. Glacial till is different from what gets deposited by running water because it's unsorted. Running water tends to separate out particles by size because the ability of streams to carry particles depends on their speed. So as they slow down, the big particles fall out first, then the smaller ones, and then the smallest ones. Glaciers drop particles when they melt, drop stuff when they melt. So there's no sorting going on. They just pick everything up and dump it. There's often examples of stuff that is scratched where they were dragged across the ice for larger pieces. And you get an unsorted mixture of many different sediment sizes. So some of the depositional features you get it with glaciers, you get moraines. which are layers and ridges of till, where the edge of the glacier is melting, so it's dumping material down and it piles up. There's a few different types of moraines. There are lateral moraines, which are running along the length of the glacier as it flows. They're like strips of sediment running through. There are medial moraines, there are end moraines, and there are ground moraines. So the end moraines are at the furthest extent that the glacier advances. So here are some of the end moraines of the most recent glacial advance. You can see they go, cover much of this area. The end moraines are down in central Illinois and central Indiana. There can also be an outwash plain or a valley train of various deposits. There are things that you can get kettles, which are rounded indents, drumlins, eskers, and caves. So eskers are sort of ridges that run across. Drumlins are these sort of little hills. Moraines are these lines of deposit. A ground moraine is sort of the stuff deposited on the ground. You get braided rivers. Commies are these hills. Kettles are these indentations. So here's a short video about the various depositional landforms from glaciers.
Hi there, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to identify, name, and describe the formation of a bunch of different depositional glacial landforms. These are glacial landforms that occur in areas of continental glaciation. Now, if you want to see where continental glaciation is taking place today, you've got basically two big options, Greenland and Antarctica. These two locations are the only places on Earth today where there are ice sheets. However, if you were to go back in time to around 18,000 years ago, you'd find that there were several other major ice sheets, including one that covered most of North America and others in Siberia and Northern Europe. These ice sheets leave behind characteristic landforms that we refer to as depositional landforms because they're made out of glacial sediment. So you can see here over on the far right, there's an end moraine, which marks the furthest point that the glacier made it out to. So we can call this a terminal end moraine. If the glacier retreats a bit, it can leave behind a recessional end moraine as well. And then it can retreat some more and leave behind this big area of ground moraine, which has various landforms in it. You can see some kames here, little piles of till. There are braided rivers crossing this landscape. There are even the casts of old rivers that ran through the glacier. These are referred to as eskers. They look kind of like long snakes crossing the landscape. And there are also drumlins. Drumlins have a big upside-down spoon kind of shape, steeper on one side and gentler on the other. Here's an example from New York State near Rochester. You can see that there's a bunch of drumlins there. Here's a topographic map depicting those drumlins. Notice how on their northern end they have very closely spaced contour lines, and that indicates that that's a very steep section. Whereas on the southern portion, the contour lines are more widely spaced apart, and that indicates that it's more gently sloping there. That's basically a way to read ancient ice direction. In this case, the ice was flowing from the north towards the south. Another feature that we discussed were end moraines. Here's a look at the American Midwest. There's two generations of end moraines depicted on this map. An earlier generation in purple, and then that's mostly overprinted by a younger generation, which is shown here in red. Notice that the younger generation tends to parallel the shapes of the Great Lakes, so the shorelines of the Great Lakes are matched by end moraines that are recessional end moraines. So the Great Lakes were carved out, in fact, by glaciers, lobes of that great continental ice sheet. End moraines can also be found in the east. You can see some over here on the shores of New York and New England. Okay, let's see which of these you can identify here in this picture. We've taken away the labels now. Take a moment to see what you can spot. All right, so we've got end moraines here. We've got a terminal end moraine over on the far right, and then a recessional end moraine a bit behind it over on the left. There's the outwash, the glacial outwash flowing down these rivers. Okay, Little lakes, we didn't mention these lakes right here, but these are called kettles. These are little spots where chunks of ice were left in the ground when the ice melted away. A little hole was left. If the bottom of that hole is below the water table, then you've got a kettle lake. You'll notice over here is our esker, this sinuous little trace going across the landscape. Looks like this esker ends in a delta here, probably fed into what was once a lake right in front of the glacier, something like that one there. We've got kames, and we've got drumlins. This whole area here is referred to as ground moraine. So hopefully you were able to pick out some of those features. Nice work, and thanks for your attention. This has been another Smart Figure.
So some of the effects of the Ice Age glacier, they had a number of effects. They caused the migrations of animals and plants. They moved various life, when ice covers everything, you're going to move away from the ice. After they melted away, they had pushed the crust down. So several places are still rebounding upwards from the release of that, like the Hudson Bay area. There was a worldwide change in sea level because all that ice melted and fed into the seas and raised the sea level up, causing things like the closing of the land bridge between Asia and North America up in the Berings Strait. There were changes in various rivers. The various ice dams would create proglacial lakes, and there are pluvial lakes. So the mean sea level dropped while all of these glaciers formed. During the last glacial maximum, about 18,000 years ago, the sea level was nearly 100 meters lower than it is today. Now it has risen up quite a bit. So the coastlines used to be bigger, things like that. So one of the effects of the formation of these massive glaciers is a drop in sea level, because all that water is moving into the ice.
The growth and decay of ice sheets significantly influences sea level and the configuration of coastlines. During the last glacial maximum about 18,000 years ago, sea level was about 100 meters, more than 300 feet, lower than at present. As you can see, the position of the coastline looked very different from today's. Here's a map of what North America would look like if present-day ice sheets were to completely melt.
Now, the Ice Ages, the Earth goes through cycles. Sometimes it's warmer, sometimes it's colder. The Quaternary Ice Age, technically, under some definitions, we are still within the Ice Age, because there are still glaciers covering, continental glaciers. But the Ice Age began about 2 to 3 million years ago. And the division of geological time is called the Pleistocene epoch. Ice covered about 30% of Earth's land area. It was twice as extensive in the northern hemisphere than in the southern hemisphere, because a lot more land in the northern hemisphere is further north, is closer to the poles. So here are the ice sheets that covered much of the northern hemisphere during the Ice Age. There's glacial ice and sea ice. There was a land bridge that formed between, because of the lowering sea levels and the ice, there was an area, there was like a land bridge between North America and Asia. So there was an exchange there. That's how humans got to North America. They got to the Americas. It's also how various animals left the Americas and got to Eurasia, like horses. So any successful theory for the origin of ice ages needs to account for both the cooling of the Earth as well as various short-term climatic changes. There are several proposed models for causes of ice ages. Things like plate tectonics, if the continents were arranged differently, There could be changes in oceanic circulation, which could lead to cooling. It doesn't take a huge change in the whole system, because you get positive feedback loops. Once you start cooling and start developing larger glaciers, that reflects away more light, which cools the Earth more. It's sort of a feedback loop. So this is a late Paleozoic ice age. The supercontinent Pangaea showed the area that was covered by global ice near the end of the Paleozoic era. And there's the continents as they appear today. So these are evidence that of the late Paleozoic ice sheets. It might be caused by variations in the Earth's orbit. The eccentricity, the shape of Earth's orbit, varies over time, and the angle of Earth's axis changes, partially because of the way that it wobbles. So changes in the past several 100,000 years are closely associated with variations in the Earth's orbit. And a small variation in Earth's orbit could lead to one of those positive feedback loops that cause surprisingly large changes in Earth itself. So as the Earth's orbit changes during a cycle that spans about 100,000 years, it gradually changes from nearly circular to more elliptical and then back again. This is a diagram that's greatly exaggerating that change. And today the axis of rotation is tilted about 23.5 degrees to the plane of Earth's orbit. During a cycle of 41,000 years, this angle varies from about 22.1 to 24.5 degrees. And that can also affect the severity of the seasons, which could lead to changes in global temperature. And Earth's axis precesses, so the axis points to different parts of the sky. So it could be that ice ages were caused by orbital forcing.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the basic theory behind the orbital forcing of ice ages. In other words, how small changes in the Earth's orbit around the sun can end up resulting in ice ages either turning on or turning off. If you were to go back in time about 18,000 years, you'd find a very different looking Earth. In the northern hemisphere, huge ice sheets would cover much of the continental landmass. In general, it was a much colder time. One of the leading ideas for what turns ice ages on and off are so-called orbital effects. And these basically are three major ways in which the Earth's position relative to the sun changes over time. The first orbital effect is shown here. The Earth's orbit around the sun is sometimes a more perfect circle and sometimes a less perfect circle. In other words, it varies from pretty much a perfect circle to a more elliptical shape. And this variation takes place over a cycle that lasts about 100,000 years. Obviously, when the Earth is closer to the sun, it's going to be getting more energy from the sun. And when the Earth is further away from the sun, it'll be getting less energy. So that orbit, whether it's circular or elliptical, describes a plane in space. And the Earth is sort of encased in that plane. But the Earth's axis of rotation is not perpendicular to that plane. Instead, it varies between about 22 degrees away from perpendicular and 24.5 degrees away from perpendicular. Today it's around 23.5. But basically what this means is when you've got a greater amount of tilt away from perpendicular, that means you're going to have greater amounts of seasonality. In other words, winter will be colder and summer will be warmer. That varies on a cycle of about 41,000 years. This is called obliquity. Finally, we have precession, which is also known as wobble. So the Earth's axis of rotation, that line in space, actually ends up pointing to different directions over time. So right now, of course, the axis of rotation is basically lined up with the North Star, or Polaris. But over time, over about 26,000 years, it'll vary and it'll point at a different section of the night sky, like the star Vega. This is kind of like a top that is spinning, and as that top slows down, it begins to wobble. So it's still spinning around its axis, but the axis itself ends up inscribing a cone in space. So when you look at the eccentricity, which has that 100,000 year cycle, and you pair it up with the obliquity, which has the 41,000 year cycle, and then you look at the precession, which is on the order of 26,000 years, you can add those different curves together. Each of those cycles ends up basically imparting more or less of the sun's energy to a critical latitude, which is thought to be around 65 degrees north, up there in the northern hemisphere where these ice sheets were forming. Well, when you pair those all together, you end up getting a final curve that looks something like this, roughly. So in other words, this purple line at the bottom is the other three curves added together. And the low spots are correlated with evidence from deep sea sediment cores that indicate the Earth was in a cold climate. In other words, that an ice age was on. And the peaks of those curves indicate times when it was warmer and the ice caps were melting back and the Earth was entering an interglacial period. And that, again, matches up with the evidence from deep sea sediment cores. So, bottom line, slight variations in the Earth's orbit around the sun end up giving us greater or lesser amounts of heat energy, which basically turns on or turns off ice ages. Thanks very much for your attention. This has been another Smart Figure.
So that was about glaciers. Now let's move on to deserts. Now, deserts are any situation with a deficiency of water. They're defined by precipitation below a certain level, which means, amusingly, the biggest desert in the world is Antarctica. It's technically a desert, even though it's covered in snow. Because it doesn't get much precipitation. It's really dry there. It's just also really cold there. So roughly 30% of Earth's land surface is desert. And the distribution and causes of dry land vary, but there's the global distribution of air pressure and wind cause belts that are warmer and drier that along, they have these high pressure belts that are drier. The deep interiors of land masses are drier because they're further from the ocean. And the high mountains can cause rain shadow deserts, where any water that was in the air them gets basically squeezed out as the air gets pushed up over the mountains. All the rain falls out on the windward side, and the leeward side ends up dry. I should be better at remembering those terms. I used to do sailing. So there's a few factors. You have these rain shadow deserts like here, where they're behind mountains. There's a rain shadow desert there. There's the strip here. And here, which is very dry. These are dry because of the wind structure. And here we have some that are like deep within the continent. They're dry. Yeah. So here are some various deserts. So here's a short video.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the two principal causes for the formation of deserts. This is a map showing the distribution of desert lands around Earth's surface. You'll notice that in the Americas, they tend to be located in the mountainous west. In Africa, there's two main belts, one in the north, one in the south. In the middle of Australia and in the middle of Eurasia, there are also very large desert regions. In every place, the desert regions are surrounded by steppe regions, which are semi-arid. Why do we find dry lands in these particular locations? There are two reasons. The first one is because of the circulation of air in Earth's atmosphere. Now, you know the equator gets hit most by the sun, which means it tends to produce lots of warm air, and that warm air rises away from Earth's surface. As it rises, it takes with it a load of water vapor, and that water vapor cools off at higher levels in the atmosphere, causing it to condense and then precipitate. So the tropics tend to be very warm and very wet. Now, the air, freshly devoid of water, ends up moving away from the equator in these big, large-scale convection cells. These tend to sink again at about 30 degrees north and 30 degrees south of the equator. So this produces the so-called subtropical high. It's called high because it's a high pressure zone because of all that air cascading downward from higher levels in the atmosphere. Now, that air is very dry, so it tends to produce belts of desert in the regions where it sinks towards Earth's surface. This is certainly the case in Africa. In the famous blue marble image, you can see basically there's a large belt of desert that extends across northern Africa and the Arabian Peninsula, another belt of desert across southern Africa, and you'll notice, of course, there's no clouds in those regions either because there's very little water vapor in that descending air. And then along the equator, which runs through the middle of Africa about right there, there's lots of clouds, and in the few places where you can see below the clouds, there's dark colors indicating the forest that's growing thanks to all the rain that falls in that area. The other reason that we get deserts is due to the rain shadow effect. And this is certainly the case in California. In California, the source of the precipitation is that it's coming off the Pacific Ocean. So as it moves eastward off the Pacific, a little bit of precipitation gets wrung out as that air mass passes over the coast ranges of California. Basically, the mountains there force the air up to a higher elevation. At that higher elevation, it's colder. That causes water vapor to condense out of the air and potentially to precipitate. Then it passes over the relatively low-lying Great Central Valley, and because there's no obstacles there to force it up to higher elevation, you don't really have a whole lot of rain in the Great Central Valley. But then there's a very big obstacle indeed, and that's the Sierra Nevada mountain range. The air masses moving over the Sierra Nevada get forced up to really high elevations. That means that the water vapor is more likely to encounter cold temperatures and therefore to condense and potentially precipitate out of the atmosphere. By the time the air gets over to the far side of the Sierra Nevada, out into the Great Basin, basically has had all of its water vapor wrung out of it, and there are no more really high obstacles to extract rain from that air. As a result, the western slopes of the Sierra Nevada look very different from the eastern Sierra. Let's go ahead and take a look now at another U.S. state. This is the U.S. state of Washington. Eastern Washington state is an example of a desert. Does this look like it would be an example of a rain shadow desert or a desert that's due to the large-scale convection that is observed in Earth's atmosphere? Well, you've had a minute to think about that. It's not really right there on that subtropical high, and so you wouldn't expect this to be a desert caused by convection in Earth's atmosphere. However, we have very good evidence that suggests that this is in fact a rain shadow desert. As with California, the source of the water is coming off the Pacific Ocean in the air, and you can see when it encounters ranges of mountains, such as the Olympic Mountains or the Cascade Mountains, you see there's lots and lots of precipitation there. And as a result, eastern Washington is a desert because of the rain shadow effect. Thanks very much for your attention. This has been another Smart Figure.
So, in dry climates, the geologic processes are a little different because water is not acting as that major source. So weathering in dry regions is not as effective as in humid regions. So the breakdown of material is slower. Mechanical weathering forms unaltered rock and mineral fragments, but you don't have some of the convenient things like frost wedging to drive that mechanical weathering, so it's not necessarily as fast. There's some chemical weathering does occur as well. Clay forms, thin soil forms, but again, because it's so dry, the chemical weathering is much slower. In arid climates, water is less common, so you have these ephemeral streams that are dry most of the time, but only flow during periods of rainfall. Because of the climate around deserts, rainfall often occurs in very heavy showers. You get huge dumps of water when you get rain. This has a tendency to cause flash floods, especially because the drainage is poorly integrated. So it picks up material, and indeed, most erosional weather in a desert is still done by running water. It's just done in spurts. So the very dry soil doesn't incorporate water as quickly. You get these creeks suddenly flooded with water, and you have these flash floods that carry a lot of material with them, and it can be quite dangerous. So most of the time, desert stream channels are dry. But shortly after a heavy shower, you can see sudden flooding, and although these floods are short-lived, they do cause large amounts of erosion. And a familiar sign in desert areas where roads dip into washes, you can see potential flash flood areas. And they can rapidly fill with water following heavy rain, and they can often carry a lot of surprisingly large debris. There's some impressive videos of flash floods where it's just like tree branches and stuff all being carried across a road, and it's seriously a couple feet high slamming across a road. So the basin and range area of the western US is a mountainous desert landscape. It's made of uplifted crustal blocks, and the interior drainage into basins produces these alluvial fans and bajas and playas and playa lakes. And the erosions of mass causes local relief to continually the local relief to continually diminish. And eventually mountains get reduced to a few large bedrock knobs called inselbergs projecting above a sediment-filled basin. So you start, you have these mountains, you have these playa lakes, you get alluvial fans forming. These will steadily wear down, filling up the basins. And eventually they'll be reduced to just sort of lumps while the basins fill up with sediment. So these are the, the tilted blocks for these sharp mountains. Then they get worn down and eventually fill up. So this is a short video about the evolution of the basin and range region.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the sequence of events that have taken place to produce the basin and range landscape, and also identify different features of that landscape. So this is what the basin and range looks like if you ever go there, and you definitely should go there because it's awesome. You can see that there is a big basin here in the middle of this view, and then off to the right there's a range, off to the left there's a range, and even in the foreground here we've got a small range. And you can see cutting across that foreground that there's some drainage. So there's both tectonic causes to this landscape, and also there are effects from weathering, erosion, and deposition of sediment. The basin and range is located in the American West, and you can see its distribution here on this map. Basically what's happened here is that tectonic extension has produced a series of north-south trending normal faults, and those have broken the crust up into a bunch of different little fragments. So these faults are normal faults. They're shown here in the cross-sectional view, and that breaks the landscape up. Notice that the blocks of crust that have dropped down relative to their neighbors have produced these basins, and the pieces of crust that are poking up into the sky are the new ranges. Now, as erosion goes to work on the ranges and transports sediment downhill into the basins, we get a couple of different features. Prominent are the alluvial fans. These are basically big piles of sediment that are produced where the canyons draining the mountains end up meeting the valley floor. If there are particularly low spots, may accumulate water, and that is present in the form of these playa lakes that you see here. If you let the landscape continue to evolve, the alluvial fans may coalesce to produce continuous aprons of sediment that basically drape the connection between the ranges and the basins. Those are called bajadas. And the lakes may dry up to produce these salt flats known as playas. If enough time goes by, the mountains may be reduced to little tiny nubbins, and they may poke up just barely through this sea of sediment. So those little nubbins that are poking up are called inselbergs. Let's take a look at some examples here. Here's a salt flat. This is the Bonneville Salt Flats in Utah. Here's an example of an alluvial fan. You can see it here leaving a range and entering a basin. Here's an example of several alluvial fans that have coalesced to form a bajada. And here's an example of an inselberg or two. So there's a prominent inselberg right here, but there's even a little one right here. Now let's take a look down on the most famous valley in the Basin and Range Province, and that's Death Valley. So in this perspective, north is off towards the right side of the screen. The bottom of the screen is the east, and the top of the screen is the west. And you can see here the Panamint Range on the west and the Amargosa Range on the east, and in between is Death Valley. Notice that there's this beautiful, well-developed bajada all along the western side of Death Valley. So that's all sediment derived from the weathering of the Panamint Range. On the eastern side, you don't see a bajada. Instead, you just see isolated little alluvial fans like the ones that we looked at earlier. Okay, time for a quick quiz. How many alluvial fans can you count here? Okay, so you had a moment to think about that, and hopefully you figured out that it was a trick question. Ha ha ha. So you might have said 1, 2, 3, 4, 5 different alluvial fans, but because they've all coalesced together here into a continuous apron of sediment, I would say there's no alluvial fans here, and instead that this is an example of a bajada. So hopefully you got that trick. I'm sorry to be so devious, but thank you very much for your attention. This has been another Smart Figure.
So that was deserts. Now let's talk about one of the other sources of erosion, wind. So wind erosion is not as important of a factor as water erosion, but wind erosion is driven by factors like deflation, where it's the lifting of loose material. This produces blowouts and desert pavement. And there's also abrasion, where that loose material carried by the wind can wear down surfaces, it will polish rock surfaces. You get the desert pavement where all the loose material is blown away, and you have this tougher, harder material underneath that remains. You can have areas that get blown out by strong winds, and abrasion will polish rock surfaces, and you can get some beautiful curved surfaces from that. And there's significant movement of dust from different places. So here's the Sahara. The movement of dust here is from the Sahara Desert over the Red Sea in Saudi Arabia. But a much further carry is that dust from the Sahara gets carried actually across the Atlantic Ocean and helps seed the rain over the Amazon basin. The Amazon rainforest is partially the rain there. Some of the nucleation points for the formation of the rain over the Amazon rainforest is dust from the Sahara. So the wind can carry dust and other lighter material. So here's a video about the suspended load of.
NASA scientists have performed the first multi-year study using satellite data to measure the 3D distribution of dust that travels from the Sahara Desert to the Amazon rainforest. The Sahara is the world's largest desert. At more than 3 million square miles, is almost the size of the continental United States. Each year, Saharan dust is lifted from the ground and transported by winds on a 3,000-mile journey across the Atlantic Ocean. A portion of the dust collects in the Amazon basin, the largest rainforest on the planet. Although dust particles are small, no larger than around a tenth of the width of a human hair, they form massive plumes that can be seen from space. NASA's Calypso satellite was launched in 2006 to study the vertical structure of clouds and particles in Earth's atmosphere. Calypso observations from 2007 through 2013 show that on average 182 million tons of dust leaves Africa each year. Of this amount, about 27 million tons is deposited in the Amazon basin.
Sahara dust contains phosphorus, which is an important nutrient for plants. In the tropic region, the phosphorus is quite limited, so it's important to estimate how much dust from desert is transported to the Amazon.
The study shows Saharan dust adds phosphorus to the soils that help compensate for losses due to surface runoff and floods. However, the amount of dust transported to the Amazon changes from year to year. According to the study, this variation is closely associated with changes in rainfall in the Sahel, a belt of semi-arid land just south of the Sahara.
When the Sahel was dry, the dust transport to the Amazon in the next year would increase. When it was wet, dust transport will decrease. Using satellites to get a clear picture of dust is important for understanding and eventually using computers to model where that dust will go now and in future climate scenarios.
So as material gets blown off by deflation, it will continue to remove finer and finer particles, and you get a desert pavement established of heavier particles that can't be carried away. And these weathered pebbles and cobbles on bedrock, the wind-blown silt will also accumulate and sift downward through coarse particles, and the silt will continue to accumulate and lift the desert pavement. So here is a video about how the desert pavement, sort of harder, larger particle desert pavement.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. In this video, we're going to take a look at desert pavement. And after watching the video, you should be able to describe the two principal hypotheses that explain the formation of desert pavement. So what is a desert pavement? Well, it looks like this. Basically, sometimes when you go out into the desert, you'll find that there is a layer of pebbles and maybe cobbles too, but mainly pebbles and coarse-grained grit. And this covers up a layer of finer-grained sediments underneath. So if you scrape away these pebbles, you'll find that underneath is not necessarily more pebbles, but maybe sand and silt or other fine grain sizes. One idea for how desert pavement forms relates to blowouts. Remember that blowouts are areas where the wind has scoured into sediment and removed a lot of it. So like here in this lower picture, that used to be the ground level there, and then the wind has scoured away all this material down below it. So how does that relate to desert pavement? Well, the idea is that you start off with a poorly sorted batch of sediment. So as you can see in the upper left here, we've got a bunch of pebbles mixed in with sand and silt. Then you let the wind blow on it, and the wind picks up the fine-grained stuff and carries it away. That means that it tends to concentrate pebbles in that upper region, basically as it washes away the finer-grained stuff and leaves behind the big stuff that the wind can't possibly pick up. By the time it ends up blowing away enough sand and silt that the pebbles are concentrated in a layer a centimeter or 2 centimeters thick, that layer ends up acting like a shield, a protective cap that ends up blocking further deflation. But in other places, there's a different hypothesis that is favored, and that is the idea that's illustrated here on the bottom, that we start off with a layer of pebbles, perhaps deposited by a stream or something like that, and then those pebbles actually end up trapping fine-grained sediment in the little spaces in between them, because there's slightly less wind energy there between the pebble grains than above them. And so they trap a little bit of sand and silt, and then over time, basically that trapping effect builds up a layer of fine-grained sediment underneath the coarse-grained sediment up top. So this idea is actually fundamentally different because it actually increases the volume of sediment over time, whereas the previous deflation hypothesis decreases the amount of sediment over time. So where does that leave us with an exposure like this one? If we were out in the desert and we wanted to figure out which of those two hypotheses produced this desert pavement, what would we do? Okay, well, you had a moment to think about it. I would suggest that you dig underneath the desert pavement. And if you find a poorly sorted deposit under there, then perhaps deflation produced that desert pavement. On the other hand, if you find just fine-grained sediments with no pebbles or cobbles scattered throughout it, then that would suggest the second hypothesis was the correct one. Good job! You are on your way to becoming a geological detective. Thanks for your attention. This has been another Smart Figure.
So there's certain types of wind deposits. You know, the wind is picking stuff up, carrying it away, but it can also deposit it as well. So you can have loess, which are deposits of wind-blown silt. These are extensive blanket deposits. The primary sources are deserts and glacial stratified drift. And the most common wind deposit that people see is sand dunes. These are mounds and ridges of sand formed from the wind's bed load. Stuff bouncing along at the surface, carried by the bed. Some characteristic features: there's a slip face, which is the leeward slope of the dune. There are cross beds, which are the sloping layers of sand in the dune. And sometimes these can actually solidify, forming sedimentary rock, which is, you get these fascinating preserved dunes. So dunes are commonly asymmetrical. They migrate with the wind. And you know, they're Then as the wind blows, they're steeper on the side that is downwind than the side that is upwind. And then sand grains deposited on the slip face at the angle of repose cause the cross bedding of dunes. You get basically the dunes pile up on top of each other as they move along with the wind. And when dunes become buried and part of the sedimentary rock occurred, that cross bedding gets preserved. So here's an example of that cross bedding in the Navajo sandstone in Zion National Park in Utah. So this is a short video about how dunes move.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the main mechanism by which wind moves sand dunes. One thing we know about sand dunes is that they don't stay put. They tend to move over time. And we also know that wind is capable of moving the very small grains of sand that compose a sand dune. If we happen to be near a sand dune on a windy day, we might actually even see sand grains moving. Here you can see little sand grains bouncing along the surface of the dune as they're carried along by wind. They're carried a short distance and dropped, and then they're carried a short distance and dropped. They're saltating over the dune surface. This is the way that wind moves dunes, one grain at a time. Wind blows over the gently sloped back sides of dunes and picks up sand grains there. Then in the lee of the dune, on the side that's facing away from the wind, where the wind energy is a little bit lower, new layers of sand grains are deposited on that face. That's called the slip face, because basically the sand grains are piled up there until suddenly they slip. This is what it looks like when they slip. There's a little avalanche that runs down the slip face of the sand dune. Many, many, many of these little avalanches end up being built out over time to produce what in cross-section appear as little lines. These are crossbeds, and we've seen crossbeds before when we studied sedimentary rocks. If the wind direction changes, say from left to right back to right to left, then the direction of those crossbeds is going to change as well. So you can see some of the crossbeds here are inclined towards the right, and then the more recent set are inclined towards the left. Here's an example of some of these fossilized crossbeds. These are in the Navajo sandstone in Zion National Park. And you can see the main beds are units like this, and then within them are these beautiful crossbeds, which are inclined in the downwind direction. So basically these are the preserved slip faces of ancient sand dunes. Okay, to test yourself here, we've drawn a little barcan dune. Make a prediction about which way this dune is going to move if we let the wind blow on it. Well, barcan dunes form in a very specific orientation relative to the wind. So if you've studied that portion of the chapter, you know the wind's got to be blowing from the left towards the right, picking up sand off the back of the dune and then dropping it on the slip face. Over time, that's going to cause the dune to move. All right, so it's not moving as a single bodily mass, but one grain at a time, this dune is going to be moved from the left towards the right, from upwind towards downwind. Thanks very much for your attention. This has been another Smart Figure.
So there's several different types of dunes. There are barcan dunes, like you saw in that image, transverse dunes, longitudinal dunes, parabolic dunes, and star dunes. So here are the different types. Barcan dunes are sort of crescent shaped and hollow on the inside. Transverse dunes are sort of the long, wavy dunes you might see traditionally. Longitudinal dunes are dunes that are in the same sort of direction as the wind. They're long and skinny, but along the direction of the wind. Parabolic dunes are arc-shaped, but sort of in the other way around. Star dunes are much more irregularly shaped, and the wind comes in multiple directions. And barcanoid dunes are another more irregularly shaped sort of version of the transverse dunes. So here's a video about the different types of dunes.
Hi, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to name and describe the 6 major types of sand dunes. Okay, let's take a look at this scene here. Here some sand dunes are moving over some agricultural fields. But what kind of dunes are they? And what do they tell us about the region in which they are found? Well, there are 6 major types of dunes that we want to learn. The first is barcan dunes. Barcan dunes are crescent shaped, And the movement of this crescent is kind of like a Pac-Man, if you remember that video game. So basically the open part of the crescent, the concave part of the crescent, is the downwind part where the slip face is. So the wind moves up the back of these and then they advance towards that crescent shape. Now these are found in areas with a moderate supply of sand, but oftentimes they're moving over bare bedrock. Transverse dunes are linear dunes that form basically perpendicular to the wind direction, and these form in areas where there's more sediment than in Barchan dune areas. So we've got a nice consistent direction to the wind, and we get these linear ridges. Barchanoid dunes are intermediate in their form between Barchan dunes and transverse dunes. Basically, they look like a bunch of Barchan dunes that have been lined up side by side. The next kind of dune we want to pay attention to are the longitudinal dunes, and they are parallel to the prevailing wind direction. So whereas transverse dunes form perpendicular to the prevailing wind, longitudinal dunes form parallel to it, except the wind direction actually has to vary a little bit. So sometimes it's from the west, sometimes it's from the south, sometimes it's from the southwest. The average wind direction is going to be parallel to these longitudinal dunes. Parabolic dunes are kind of a special case. They form in areas where the sand is somewhat anchored by vegetation, and oftentimes wind will be coming off of a body of water, a lake or the ocean, and it'll slam into these semi-stabilized dunes, and it'll create an area of blowout. So even though these are crescent-shaped, kind of like the Barchan dunes, here the slip face is on the convex side of the crescent. So the open mouth here is actually facing in the upwind direction, opposite from the Barchans. Finally, there are star dunes, which have lots of little ridges that emanate out from a central point, and these form in areas where the wind direction is variable. Okay, take a look here. Here's a little aerial photograph showing a beautiful landscape. What sorts of dunes do we appear to be looking at here? You might say it doesn't really look exactly like any of those pictures that we just looked at, but I think the one that comes closest is Barchanoid, because basically you can see these crescents that are steeply inclined, so those are downwind, and so therefore the wind must be coming from the back of the picture towards the front. But those crescents are all kind of lined up in a row in more or less linear ridges. So that indicates, I think, that the best name for these dunes would be Barchanoid dunes. Thanks very much for your attention. This has been another Smart Figure.
And that is the end of the chapter. So that is it for lectures for this semester. So Tuesday next week, we will have the test on chapters 6 through 9. And then after that, starting Thursday next week, we will be doing the presentations. So make sure you have your presentations done by the 4th. And make sure you submit your slides so that I can pull them up so you can do the presentation in class. Yeah. Have a nice day. I will see you all in a week, because we don't have class on Thursday.